Okay, so hi everyone, thanks for having me. I'll talk today about some ideas on emergent abilities and simple training data statistics. If you have any questions during the talk, please feel free to interrupt me and we can have it interactive. Okay, so emergent abilities is a concept that was introduced a few years ago in the field and was talked about in the context of large language models, where you can increase the size of the model or the amount of training data used to train these models, and suddenly you see a behavior that was not observed before. So here are a few examples of different kind of tasks where you can basically see where we increase the size of the model size and there's basically no improvement, and suddenly after a certain size, a sudden increase in performance. And there's been a few papers on the topic and exploring this idea and showing that it often happens in scale both of training data size or training flops and model size. And this is a definition from NaNData from iClear 2023 that says that neural networks often exhibit emergent behavior in which qualitatively new capabilities arise from scaling up the model size, training data, or number of training steps. And yeah, these are some other examples, and yeah, basically you see the same kind of behavior. So once you increase the size enough, you suddenly get this kind of large improvement that was kind of hard to anticipate before. And then came this paper, our emergent abilities of large language model Mirage. This was news 2023. And basically what they said is that emergent abilities are a mirage. They're not a real thing. And it really depends on the way that you measure progress. And basically what they showed here is that depending on the way that you define your metric, or the metric that you look at, emergent abilities basically disappears. So basically what they said is that instead of looking at discrete metrics like accuracy, where just you ask whether something, whether the task is successful or not, you can break it down to something more continuous. So for instance, if you look at the loss or other kind of metrics that are simpler than the high level task, suddenly you see a much smoother increase in performance. So in this talk, I will talk about two different kinds of emergence that we can think about as a way to look at them as both discrete, that if we look at the discrete metric, it will seem like emergent ability, but we can also look at it as a more continuous variable where suddenly there's no emergence and it's following a clear trend. So the first one is about linear representation of factorial relations that they happen to form based on the relation frequency, and this is what we find. And a nice property of that is that once the model has seen enough training instances, or here we look basically at co-occurrences of entities, so once the model has seen enough of those entities appear together, it suddenly has this kind of capability, or here this kind of linear relationship form in the hidden representations. And the second kind of capability or emergence I will talk about today is the imitation of concepts. So how concept like an art style or a face, or the ability to generate faces or other kind of concept form according to concept frequency. So we will look at how many training examples of a certain concept happen in the training data and how it allows the model to be able to imitate such concepts. Okay, so the first paper I'll talk about today is this one on linear representation and pre-training data frequency in language models. This I'm going to iClear next, and I'm going to present it this week. And this work was led by Jack Merulo. He's a final year PhD student at Brown. He's graduating soon, and he interned with us at A2 last summer. And this is a joint work with Noah Smith and Sarah Wigefe. Okay, so before I go into the details, let's start by talking about linear representations and what does it mean. Okay, so language models, they typically are trained on a lot of data, so a lot of pre-training documents that typically the standard loss, at least the initial loss, is to, or objective is to predict the next word in a sequence. So after we train this model, they happen to learn different kind of capabilities. So sentiment is one of them, right? So we can give a sentence to a language model and it will have, if it has learned this kind of association between positive and negative words. And another thing is facts. So this model capture a lot of knowledge about the world from all the training data they have seen. And a lot of it is about facts, right? So like the fact that Paris is the capital of France, or Beijing is the capital of China, and so on. So if we look at facts, so like Oracle's headquarters is in Texas, right? This is the sentence that can appear in the training data. We are interested in this kind of subject relation object triplets. So we can think about it as a function of what is the, if the function here is headquarters in, so if we give it Oracle as an input, we would expect to get Texas as an output. And this is kind of the more high-level relation. And an interesting observation that people have made before is that these things can be linearly represented. So there might be some linear mapping between S and O, between the subject and the object. And we would say that this is this linear relationship is robust if we can have this transformation that robustly transform every subject to an object with the same kind of transformation, with the same function. Okay, so for now, let's say we have, so we have this paper from Pacanaro and Hinton from NeurIPS in 2001, and basically what they try to learn is this kind of function, W, which here is a matrix, that when you multiply it by S, by the subject, you get the object. And there's a lot of insights and benefits to having this linear relationship. They're often more interpretable and they're very useful in practice. And then this paper came from ICLR 2024 last year, and they basically looked at a very similar idea, but in the context of language model or large language models. So basically they came up with this concept of linear relational embeddings, or LREs. And the basic idea is that you can, you want to find this W, this transformation matrix W, that when you multiply it by a subject S, and here you take some hidden representation from the internals of the model, and you multiply it by this function W, by this matrix W, you'd get O. This is what you want to get. And you can test it on new data, right? So you have, you can test it on, you can train this transformation on a small amount of data to extract the object O. And then if you can generalize on new objects, you would say that you capture this kind of linear relationship. So we take those hidden representation, like the representation of Miles Davis, and this is some internal representation that we get. We multiply it by matrix W, and we try to predict the object O. In practice, they learn this matrix using Jacobian matrix mapping, that we have a small amount of training data. Here, n equals 8, so it's not a lot of data. So you learn this transformation, or you find this transformation, and then you can check how well it generalized to other kinds of objects, right? So if previously I showed you that we learned it, let's say, on Miles Davis, that he plays the trumpet, now we can take this matrix that we learned, we can apply it to new data, and then if we get that we are able to make Cat Stevens predict that he plays the guitar, so this would mean that we learned, or we found this kind of linear representation because we were able to transform it with a linear transformation to the correct object.
I have a question about claim and model thinking LRIs. Do you mean that there are some relations implemented in this way, or all the relations are implemented in this way?
Yeah, so we'll talk about that later, but let's say for now we're only looking at one relation at a time. We learn this transformation per relation, right? And we will soon see that sometimes this relation, we can find this transformation very well, so it will be almost a perfect transformation for all of that data set for that relation.
But there are a lot of other relations that must be implemented in nonlinear.
Right. So I will get to that. I will get to that.
Yes, in the linearization, is it different from the compositionality of language or linguistics?
Can you?
Compositionality,
Mm-hmm.
that is something, relation and object,
Yes.
relation, subject, then object. This kind of relation is, say, captured by in linguistics compositionality, composing some part, makes sentence, meanings, that kind of thing.
Yeah, I think it's related. I think with compositionality, you can also think about more complex kind of functions. And I think that once you have certain relations or function encoded in a linear way, this can lead to more complex computation and make more compositional functions. Okay. So I showed you how we can learn those LREs, and now let's talk about how we measure that. So for the metric, they proposed a few metrics, but one of the main ones that we will also use is basically we want to talk about generalization, right? So we want to find this matrix W, which is the transformation function, and let's say we have the model. We were able to find this transformation between Miles Davis plays the trumpet, and now we want to check whether we can change it that the model would predict Miles Davis played the guitar, right, instead of the trumpet. So we will take the hidden representation from the language model with Miles Davis, and then we change it to something else, let's say the representation of Cat Stevens. And if we're able to change that such that the model would produce a guitar instead of trumpet, this would mean that we're able to find this linear relationship, right? Because we can just switch it and get the new prediction that we expected it to make. So this metric is called causality by the LRE paper, and basically what we check in practice is whether the probability of a guitar after the transformation, after this counterfactual intervention, would be higher than trumpet, which is what it was originally. Yeah, so this is causality. Okay, so now we took this idea, we implemented it with Olmo, one of the language models we developed at AI2. And we show here the results across many different relations. And on the y-axis, we see the causality score, and on the x-axis, those are the different relations. And overall, you can see that there's a wide range of results, right? So more on the left, we see very high scores of causality, meaning that those relations are linearly encoded. But on the right, they're very close to 50%, meaning that those transformations are probably not linear, and we're not able to transform them. And then the question that arises is why, right? What's the difference between those different relations, and whether we can say something meaningful about them? All right, so we talked about those linear transformations. So now, what makes the model encode some relations in a linear way and some others not? Okay, so these are basically the basic questions that we asked in this work. What factors of the pre-training data lead to the formation of linear features of some but not all relations? And when do those linear relations form or emerge in the pre-training state? Okay, so let's talk about the setup. We look at 25 factual recall relations, like headquarters in, and overall, we looked at 10,000 unique subjects and objects pairs out of all those relations. And for the data sets, for the models that we use, so we use Dolmo. It's one of the large language models that we developed at AI2, and Dolmo, which is the pre-training data used to train this model. And we also looked at GPT-J and the pile that it was trained on. Okay, so now we have this hypothesis that there is some relationship between the pre-training data and the fact that those linear or that those relations emerges in a linear way in those models. So concretely, our hypothesis is that if the model was trained on many subject and object that co-occur together in the training data and basically shows those kind of express those relations, these linear features would form and we will be able to extract them. And in practice, what we actually want to look is whether the relation is expressed in the data, right? So like whether, let's say Miles Davis plays the trumpet, we want to count how many times it appears in the data. In practice, it's pretty hard to do because there's a lot of linguistic variability, and we want to scale it to trillions of tokens. So in practice, what we look at is the co-occurrences of the subject and object, right? So instead of Miles Davis plays the trumpet, we'll only look whether Miles Davis appears together in the same document with trumpet. And there was a paper a few years ago that basically said that this is a good proxy, that there's a very high correlation between those co-occurrences and the expression of the relation. So this is what we'll look at in practice. Yeah, this just showed that the linguistic variability. So those are two different ways to express that Paris is the capital of France and another relation. Okay, now we move to the point of how do we count those co-occurrences, right? So if, let's say, we want to look at the entire training data and the final checkpoint. So this here will be on the right. One way to do this is using what's in my big data. I'll talk about this paper a little bit afterwards, but basically it's a kind of index that we have of the data set of Dolma, and using that we can quickly get accounts of different terms that appear in those documents. But another thing that we would like to do is to run this on different checkpoints. So not only on the final checkpoint of the model, but also during the process of training, we have different checkpoints that we store and have access to. So ideally, we would also look at those checkpoints and check how much those linear relationship appears there. But this is a bit harder because we don't have an index of those checkpoints, right? So there's a lot of, it's not the entire data set, but just a subset of it. So the question is, how do we count those, how do we get those counts for those checkpoints? So what we did, we wrote this library, batch search, where basically we're able to count terms in the training data batches for any training step. And we basically were able to reconstruct all the training batches for Olmo and count those terms in those sequences. And we wrote this library in Python, so it's very efficient and we can run this very quickly on the entire training data. Okay, something that's important to note, when we train models, large language model, we typically do it in batches, meaning that we don't just take each document on its own and train on that. We batch them together to maximize the utility of the GPUs that we have. So one thing that we wanted to make sure is that we will count correctly, right? So if we have that each row here is a different batch, and the columns are the sequence dimension. So if we have token 1 and token 2 in those different batches, this one we would not count as co-occurrences, even though they were trained together. But if they are in the same document or the same sequence dimension, this is what we would call a co-occurrence. So this is just a side note. Okay, so now let's move to the results. We start by talking about the causality versus co-occurrence, right? This is the main idea of the paper. So on the y-axis, we see the causality performance, and on the right, and the x-axis, we see the subject-object co-occurrence in log scale. And we basically observe a very high correlation of 0.82. So this is quite interesting. We found this kind of correlation between the counts in the pre-training data and the causality score that measures some form of linearity. And here on the left side, we see that this is one of the relation, person-mother, that is apparently not very linearly encoded. And on the right, we have country language, which is quite linear, and there's also a lot of occurrence. Okay, so far we talked about those linear features, and we showed that the linearity of relations is very highly correlated with the subject-object co-occurrences in the training data. But another question to ask is, when do those emerge, right? So is there something, does the model have to be of a certain capability, of a certain quality in order for those relations to emerge? So we wanted to look at different checkpoints of the training data. Well, those are the different checkpoints that we looked at. 550K is the final checkpoint. And this will allow us to look at different instances of the model where it's not, the best quality, right? Because it was not trained on the entire training data. And because of the search batch that we implemented, we can also do it in a very efficient way. So here, this is the course of training. So basically the red is the initial checkpoint that we looked at, and the pink is the final checkpoint. And this is the same graph as before. So x-axis is the co-occurrence counts, and the y-axis is the causality. And we can basically see that there's still a very high correlation, and like as the training continues, we get more and more higher and higher causality score. So this is only for one relation, but then we can do it for all the relations that we looked at, and the trend is pretty similar, right? So no matter when, what is the checkpoint of the model, the main factor that contributes to the model's ability to represent relations in a linear way is just the co-occurrence counts. Right, so this means that the quality of the model is not important for how well the model will represent those relations in a linear way. And another nice thing that we can get from this kind of result is some kind of threshold. So let's say we want that we consider a relation to be represented in a linear way if it's above 0.9 in causality. We can see that the threshold for this to become true is about 3,000 co-occurrence tokens. Okay, I talked about that. Okay, so basically so far we showed that the frequency is the most indicating factor of the formation of linear features in models. And now the next thing that we ask is whether we can reverse that, right? Whether we can predict frequency just from those linear relations. And one application of that idea is that even if we don't have access to the training data, and this often happens when we have those open source models that are open source, open weights, but not open data, like the Llama model from Meta, for instance, we can still say something about the training data, but just based on the weights. So this is a pretty good idea, right? So, okay. So basically what we want to do is take those linear relations that we found, and we can do it because we have the weights of the model. And now we will use different features in order to extract the co-occurrence count. So for the baseline features, we use the log probability that we get from the language model, and as well as the accuracy. And we will then use the LRE features from the previous work I showed you, like the causality scores, in order to predict the counts in a better way. So here's the result of the baseline. Basically, we don't use the LRE features, just the accuracy or the log probabilities from the model. And the fit is really low, so this doesn't really work. But then when we use the LRE features, we suddenly get a much better fit. So this is still not super high, but like it's much better than before, and we get a pretty good signal. Okay, so okay, another nice property that we get from this is that this seems to also be pretty model agnostic. So we evaluated on 2 different models, and we're able to take to fit the regression on one model, like Olmo, and then test it on the other model, on GPT-J. And if we know the size of the training data that we use to train this model, so we can also scale the result by the total number of tokens if it's available, and we get a slightly better result. Okay, so now the question is whether it actually generalizes, right? So we take this regression model that we trained on Olmo with Dolma, that was trained on Dolma, and then evaluate it on GPT-J, which is a simulation of another model that we don't have access to. In this case, we do. So this is just for the evaluation, but this is the thing that it's supposed to simulate. Okay, so the results for if we only look at GPTJ, we train and evaluate on GPTJ, we get a fit of about 0.4. And if we take the results from that we train this regression model on normal and then predict on GPTJ, we don't get as much good performance, but it's still pretty high and much better than without using the LRE features. So this was the result for this was the result for predicting the subject-object occurrences, and this is just for the object occurrences, which is a bit lower, but still like a decent amount of performance. Okay, so these are I'll show you a few examples of concrete numbers that we get. So this is for the relation of when to university at. So the ground truth for Emma Watson and Brown University, they appear together 80,000 times. Sorry, they appear together 420 times, and our prediction was almost 4,000 times. And just to predict Brown University, it appeared 80,000 times. We get 57,000 times. So there is some difference, right? But it's also not that far away. So we also looked at another metric, basically the accuracy within one order of magnitude. And this is a pretty generous metric, but it's somehow better way to reflect whether the model is actually getting in the right range. Okay, so this is this new metric, and we have here the baseline in the dots, and basically the results are around 60% accuracy when we use the LRE features, which it's not bad. So this is for just predicting the object occurrences, and this is for the subject-object occurrences, which is quite high, so about 80%. Here's a few other examples. You can often see that like the range is pretty decent. Okay. So to sum up this part, we show that language model actually encode a lot of information about the training data, and we can extract it with LREs. And we show that there's a very strong correlation and relationship between linear features and the entities frequency that appear together in the training data. And we introduced this new method for predicting the term frequency in the pre-training data, even if we don't have access to the training data. And this is, I think, a very powerful idea. Okay, another thing that we found is threshold for linearity. And this is another example of if you look only at linearity as a binary variable of like if it's, let's say, more than 90%, you would get this kind of impression of emergence. But if you look at a softer metric like causality, you can actually see a clear increase. Okay, so now I'll talk about a different kind of threshold. This will be about imitation. And if you've followed media in the past few weeks, you probably saw a lot of those Studio Ghibli images that the GPT model is able to do now. And the question is, okay, like if it's able to imitate the concept of or the art style of Studio Ghibli, how is it able to do that? And we want to connect it again to the training data. So I'll talk about the imitation capabilities. So here's an image of Leonardo DiCaprio that I generated with one of those text-to-image models. And this is the real image of Leonardo DiCaprio. So they are pretty similar, right? And here's another image that I generated with ChatGPT. And can you guess who that is? Probably not. This was supposed to be me. So the model was able to imitate Leonardo DiCaprio, but it wasn't able to imitate myself. So why is that the case? What's the difference between Leo and myself? Well, there's probably a few, but here's one of them. So here's a graph of the number of mentions that Leonardo DiCaprio versus me appear in Lion, which is one of those image captioning datasets. So I actually do not appear at all in the data, but Leonardo DiCaprio appeared about 80,000 times. And just to recall, the model was not able to imitate me, but it did in the case of Leonardo DiCaprio. So the question that we're asking here is, what if we could find an imitation threshold, which is basically the minimal number of times that a concept like a face of a person has to appear in the training data, so the model would be able to generate it and to imitate it correctly. And why is it important? So one reason is for copyrights. So this is one of the not the best example, but this is an image from a famous artist and an imitation of him on the right. There's a lot of lawsuits at the moment against models like against companies like OpenAI that are able to generate those kind of images. Another reason why we should care is about privacy. So this is the image of Leonardo DiCaprio, which is a celebrity, and it might be fine to be able to generate him. But me, I'm myself a private individual, and I care about my privacy, and maybe I don't want this model to be able to imitate. So this is the paper that we wrote in order to try to answer this question, and it's currently under submission at ICCV. It was led by Sai Verma, one of my collaborators at UW, and a bunch of others collaborated. Okay, so for the question formulation, we want to talk about counterfactuals. So we know that Leonardo DiCaprio appeared about 80,000 times in Lion. And the question that we want to ask is, what if the model would have been trained on a different kind of lion, on the counterfactual data set of lion, where Leonardo DiCaprio only appeared 100 times instead of 80,000 times, how would the model perform? Right, so we can have a look at it in this kind of formulation. So what would be the imitation ability of the model if we make an intervention on the number of times that a certain concept like Leonardo DiCaprio appears in the training data instead? So one way to approach that is using the counterfactual modeling approach. Okay, so this is the simplest approach that we can take, changing the least amount of things and answering this question. And how would it look like? So on the x-axis, we have the concept frequency, so how many times Leonardo DiCaprio appears in the training data. And on the y, and we can measure that with basically the tools like what's in my big data that I'll talk a bit later, but it's basically this index that I mentioned before. And on the y-axis, it's the imitation score. So this is basically the based on similarity between the training images of that concept and the generated images that we get from the model. It's based on some embedding similarity metric. Okay, so let's start with Lion 5B, the original data set that we trained this model, and we know that Leonardo DiCaprio appeared 80,000 times. So now the basic idea is that we want to create those counterfactuals data sets, so the Leos. So here we want to change minimally as least possible, to make the least amount of possible changes. So here we'll start with Leo 0, which is basically an equivalent data set to Lion 5B, but instead of 80,000 times of Leo, there's none. But everything else is the same. Right, and if we were to train this model, so the model has never seen Leonardo DiCaprio, the imitation score of that model would be very low for Leo, right? Because it's never seen it before. But now we can continue and train more of these models. So we'll have Leo 1, which is also probably not enough images for it to imitate it, and Leo 4 and Leo 8, and so on and so on, until we find a point where there's some change, right? And this point is what we would call the imitation threshold, where the model has seen enough training examples in order to imitate that concept. The problem with this approach is that this is very expensive, right? Because even training one of these models can cost tens of thousands of dollars, and this is only for one concept, so we'd have to do it for different ones, so this is not a viable approach. So the counterfactual solution, counterfactual modeling is not viable here, so we'll look for another solution, and this is the core idea of the paper. We came up with this approach called mimetic square, and it relies on the observational data. So the idea is that we want, instead of making those interventions in the training data and then training another model, we would look at observational data. So we only have one model and one data set, and the idea here is that we look at different concepts. So we start with Leo again. We know it appears 80,000 times and the imitation is pretty good. But now we find basically another concept. So here it's another person, Lee Reeve, that appears about 50 times in the training data, and the imitation score is not very good. And the key concept here is that we assume that there's no much difference between these two people, right? They're both humans. They kind of maybe look similar, and there's not a reason to believe that. The assumption is that if we were to train another model on Leonardo DiCaprio that appears the same amount of times as Lee Reeve, it would get the same imitation score that we do get for Reeve. So we can populate now this graph with different people that, again, the assumption here there's nothing really inherently different about them, and generate this graph, and then again find the imitation threshold by finding the point where there's a change. And there are a few assumptions that we have to make in order for this to work. I can elaborate them on the end, but this is the basic idea. Okay, so the overall approach looks like the following. So we start with a bunch of prompts for those different relations. We collect a data set with different people. We then feed it to this one of those text-to-image models. We generate a few images for each one of them, and we can then compare the similarity between the real images and the generated one, put it on a graph, and then find the imitation threshold. Okay, so let's talk about the setup now. So basically we looked at two different domains, human faces and art style, and we collected two different data sets for each one of them. And overall we looked at three pre-training data sets, so around 400 million 2B and 5B, and 4 different models that were trained on those data sets. And these are the results. So overall, the imitation threshold that we estimate is somewhere between 100 to 650 images. This was pretty surprising to us. We thought that it would be much higher. And there are also a few interesting trends here. So for instance, for SD 1.1 and 1.5, the imitation score is exactly the same. And noticeably, they were trained on the same data set. Another thing that's interesting here is that within the same domain for different data sets, the thresholds are a bit different. So for instance, for celebrities, the thresholds are consistently higher than the one for politicians. And when we actually look at the data, politicians often look the same, right? So they're all wearing suits, they're all looking straight to the camera, whereas celebrities have much more variety and difference in the way that they look, the way that they dress, and so on. So the variance here is probably a big explanation for the amount of difficulty to imitate a concept. This is how the actual plots look like. So it's a bit more noisier than what I showed you before, but it's still there's a pretty consistent trend here. In the beginning, the imitation score is really low, and then they go up. And there is some noise here, and I would like to share with you some of the reasons for that noise that we could actually explain, and some of the difficulties. So one thing is that this is the variance that I talked about, right? So this is Samuel L. Jackson, and you can see he looks here very different based on the different movies that he acted in. And when we generate those images of Jackson, we see that there's a quite similar trend, right? So like he looked very similar in all of them. So he's wearing glasses, he's on the older side. And this was one of the challenges we had to face with, and we had we basically had a way to find the most similar images from the training data within the set of his images to fit it into to make sure that it fits the generated images. Another problem that we faced is that the way that we count, right? So here are images of where the caption contains the term Marilee Pfeiffer, which is the mom of Tom Cruise. But actually, in one of those images, she doesn't even appear. So another thing that we had to take care of is that to actually look at the images and filter down images where the person does not appear. And here are some examples of how we can explain the variances. So here's an actress called Tandy Newton, which from our data set we had her name, and we looked at the training data to look for her. but she also have a different alias name, Tandiwe, which messes up things. So basically one of the kind of outliers that we had on the left side of the imitation threshold is that the score that we get is much higher than we expected. And if we adjust for that, so if we have all of the aliases, we can basically move it more to the right. And the other kind of outliers that we had is basically the opposite. So here's another person, Casey Cobb, that in a lot of her images in the training data, she appears with other people. So she doesn't appear on her own. And this makes the imitation much harder. So this is kind of the other kind of outliers that is on the right, typically on the right, where we do have a large count, right? Because she does her, she is mentioned a lot in the training data, but actually because she always appears or mostly appears with other people, it becomes much harder to imitate her concept because the model need to see more and more of her images in order to do that. Okay, so to sum up this part, we proposed a new task, finding the imitation threshold, and proposed a method for it to estimate the imitation threshold using observational data. And we found some interesting results that the threshold is somewhere between 100 to 600 images. Okay, I would like to spend a few words on open source language models and tools. So basically all of this work wouldn't have been possible without access to models and training data. So one important part is open models, and this is real open models that include the training data. And I was fortunate to work at A2 and to be part of the Dolma and Olmo efforts. And the second part is about the right tooling that is able to scale. And these are some of the work that we did, or from my colleagues at UW. And these are really important to have access to this data and to be able to scale it up to real scale. So this is just a mention again of Dolma and Olmo. They both got a best paper for resource and film awards last year at ACL. This is Olmo 2, which is the follow-up, and Olmo 3 is coming up soon. And this is just a note on the tool. So this is what's in my big data. I mentioned it a few times today. One of the key properties is that we have an index of a bunch of different data sets that we can then access and query in a very easy way and fast way and it scales. Okay, there's the part of the indexing here. So we mostly use the Elasticsearch in this work, but we also have a follow-up work where we found some automaton that we were able to index it in a very efficient way and to basically have another way to create the training data. And this is a recent paper. I think that's Yokoi, hoping I'm pronouncing his name right. Also from Weekend that proposed another way to do indexing that is a softer way. So traditional indexing of hard queries, so you only look for certain strings, but this is another really nice way to do it in a softer way. Okay, so some final thoughts on the kind of work I presented today. Why should we even care about this kind of relationship? So and features that I talked about today. So the first reason is that just from a purely scientific way, they're simply interesting, at least for me. But a more concrete thing is that we can use them in order to learn something about model behavior. And the other nice part of it is that we can also use that in order to reverse engineer the data and learn something about the data just based on the model, even if we don't have access to it. So to sum up, I talked about investigating emergent behavior, and depending on the way that we measure them and we look at and the metrics that we look at, it can be emergent or predictable. And they teaches us about more capabilities like the linearity of relation in the representation as well as imitation. And the nice part about both of them is that they can also teach us something about the data. And yeah, that's it. Thank you for listening. Happy to take any question.
Thank you very much for the talk. I have two questions. The first one is about the first part. Because you showed some equation W times S equals O. I wonder, because I have so many unique subjects and objects, so what procedure do you use to process the multiple token subject?
Yeah, so in practice, we look at a representation at the end of the subject. So if there's multiple tokens, we just take the last one.
Okay, I see. So first they use the language model to process.
Yeah, so it's everything.
The hidden.
Yeah, we take an internal representation of the model. So no, we don't look at just the embedding of the token. We look at the representation that after it's being fed to the model.
Okay, I see. So, and then for the second part, have you considered to use the difficulty of unlearning and the difficulty of relearning after unlearning, because that's also very related to the exposure frequency.
Yeah, we didn't look at unlearning in this case, just the learning part. But yeah, it's an interesting connection. I think there's a recent work that also talk about unlearning and how much it's affected by actually like how much by the frequency in the training data.
Yeah, so I wonder maybe if you because currently if you use a certain other task vector to model to unlearn it, of course you can successfully unlearn it. But if something really appear in the training data so many times, by unlearning you just destroy the last layer,
right.
And it's very easy to relearn it. But if something is very like low frequency, after unlearning it, it's not easy to relearn it.
Right.
Maybe it's somehow related.
Yeah.
Okay, thank you.
This is very interesting idea. Realization is limited between one sentence.
Sorry.
Realization
Yes.
is limited within one sentence. By the subject object.
Not necessarily. I mean, in practice, what we look at the data is in representing one sentence, but you can. It's eventually a sequence, right?
Yeah,
so like it doesn't matter.
Yeah. So if it spans many sentences, like 10 sentences, or even one paragraph or so.
So the kind of function might be a bit different, right?
Yeah,
we might have to adapt the function, the linear representation to fit that.
So the question
in this work, we look at simple.
Yeah. So my question is, what kind of realization, what types of realization is found if the span of the sentences is very long? That's my question. For instance, much more complex relation is you can find.
Yeah.
But,
we didn't look at it in practice. We only looked at relations that are presented in a single sentence. But it's an interesting question for our work.
Can linear representation be formed for low frequency counts through targeted training strategy or architecture modification?
Could you repeat the question? Sorry.
Can linear representation be formed for low frequency counts through targeted pre-training strategy or architecture modification?
Yeah, so in practice, we show that the number of occurrences of entities doesn't have to be that much for those relations to appear. So if you look at the threshold of, let's say, 0.9 for causality, the metrics that we look at, in practice, depending on the size of the model, about a few thousand instances is enough to form those linear relations.
Thank you. Any other question, comment from Zoom?
Second topic, imitation threshold. There are many contents, including both images and description languages. So combining language and image is very helpful to find the good threshold. Is it okay? This kind of thing is okay, and you can find this. You utilize this kind of to the image sentence complex.
Yeah, so in practice, the model that we look at, they have a pre-existing language model component, which is frozen, so it's not trained at all. And then you only train the image component. But it does bring a related question of the connection between how these two models combine together, which I think it's a very interesting question. But in this work, it's like focusing on the image part because the text embedding is further.
Maybe that's why the direction is, I think, very promising. So I hope you are good result in the future.
So we are concluding this call. So
Thank you.
it's Steve again.